Welcome back to Introduction to Machine Learning. I'm Ludwig Bothmann, and in this video I will give you an overview on hyperparameter tuning. You should understand the main idea behind tuning. We will speak shortly about how to fulfill the untouched test set principle via nested resampling, and also touch very shortly on pipelines. First of all, what is tuning all about? Tuning is the process of finding the best hyperparameters. We denote those hyperparameters by lambda, and those hyperparameters are different from the parameters that we have seen earlier. Parameters denoted with theta are model parameters, and hyperparameters are parameters of the learner, so one step before getting the parameters. In this guitar analogy, consider the following. So if you want to play a guitar, it's advisable to tune this guitar before you play. And similarly, you should tune your hyperparameters before playing around with your machine learning algorithm, the learning algorithm. So learning the best parameters is playing the guitar, and tuning the guitar is learning the hyperparameters or finding the hyperparameters. So we have two processes which are nested inside each other. The inner process is about finding the best parameters theta hat. You already know that you need some training data, you need a learner and learning algorithm, and in this learning algorithm you have to fix beforehand the hyperparameters lambda. And when you have the training data and the hyperparameter configuration, then you can use, for example, empirical risk minimization to find the best parameters of the model. So in this example here, find the best split points for a classification or regression tree. So then in the end, you have your trained model. But as already said, before you can train your model, you have to set the parameters, the hyperparameters of the learning algorithm. So there is a outer loop which tries to find the best hyperparameters. The best hyperparameters, because these are an input to the training algorithm. For this, you need a separate test set, because of course we have to adhere to the untouched test set principle here as well. Why does tuning matter at all? You could think perhaps it's not necessary at all, just use some default hyperparameters and hope the best, because empirical risk minimization or the training process will find the best model. But it's not the case. So a lot of machine learning algorithms like CART, K-NN, random forest, neural networks and so on have a lot of hyperparameters, and some of them are very sensitive to a good tuning of those hyperparameters. So for example, the decision tree has the hyperparameter max depth, so how deep you want to grow these trees, or this one tree in that sense. And here on the y-axis we see the test AUC, area under the receiver operating heuristic curve. And it seems that for this data set, it is better to have a higher max depth than the lower max depth, because test AUC is better there. Also, k nearest neighbors is a hyperparameter. The number of nearest neighbors k, also the distance metric, but here we only see the number of neighbors k. And the support vector machines also has a couple of hyperparameters, and as you see, there is a combination which seems to be better than this combination here in the lower left corner. Is tuning hard? Is it easy? It turns out that tuning can be rather difficult, so it doesn't have to be difficult for all the learning algorithms. But the problem is that this is a black box optimization problem. So the question is, how can we measure and compare the performance of different hyperparameter combinations lambda? So just to fix the notation here, the small lambda is one concrete hyperparameter configuration, and it is capital lambda is the hyperparameter space, analogous to capital theta, which is the parameter space of the model. So we need some black box optimization techniques to optimize the hyperparameters. I will just show you two examples here of these optimization techniques, namely grid search and random search. And the goal of these approaches is always to find the best configuration lambda star, which leads to the best generalization error, so the smallest generalization error on, of course, new unseen test data. As you see, grid search just applies a grid to the hyperparameters, hyperparameter 1 and hyperparameter 2. So you just have this rectangular structure here, and random search, as the name already says, just draws random points from the hyperparameter space and tries out those different hyperparameters and sees which of those configuration performs best on test data points. But there are also other approaches, which you will see later. Okay, now let's say we are done with that. With this, we have found a hyperparameter combination lambda star, which is the best that we could find. Okay, we did this on a test set, so we are sure that we are not overconfident or have some information leakage at some point. And now the question is, how well does this perform? So how well does a model trained with this hyperparameter combination perform on new test data? And the problem now is that we already used the test data that we had for tuning the hyperparameters. So we need a second test data set to adhere to the untouched test set principle for estimating the generalization error. Okay? So we have two different goals, or now we just have one goal left, but in the beginning we had two goals. So first we wanted to optimize the hyperparameters, and then we want to estimate the generalization error of a model that was trained with this hyperparameter set. So basically in the end we have to do a three-way split. If you look at this here, so we still need some train data, we need some validation data for finding the best hyperparameter combination, but then we take all of this and say, okay, let's train a new model on train and valid together and just evaluate this on a new test set. So we only do this once after having tuned the hyperparameters. So for tuning the hyperparameters, we can look at this validation data set as often as we want, more or less, but then we are only allowed to look at the test data set once after tuning and only with this best hyperparameter combination. And well, as holdout split in train and test is not always the optimal choice for resampling technique, and we've seen bootstrap, subsampling, cross-validation and these things. Now we can also think about how we can optimize this three-way split into train, validation and test, because of course we have the same problems as before. And it turns out that, well, we can just do this, we just have to nest these resampling techniques. So in the end we have nested resampling, and we can nest whichever resampling techniques we want to nest. So we can say train, val, test is already nested resampling, but we can also nest cross-validation, for example. And this is here a sketch of how nested cross-validation works, and I will not explain this now because we have a separate video for this, but just that you have already seen this once. And finally, let's touch shortly on pipelines in machine learning. Pipelines are there for automating the sequence of data processing and model building tasks. So the good thing about pipelines is that first of all you have a very streamlined workflow, so it's automated. From first touching the data while using some pre-processing techniques, over tuning hyperparameters to model training, evaluation and so on. So you always have the same workflow there. And it's reproducible then in the end. Because if you do some data pre-processing and then you do some hyperparameter tuning and some model training and you don't really connect these things, then it's hard to reproduce those if you want to reproduce it later or if others want to reproduce those later. And of course, the hope is also that you minimize errors in this pipeline. So human errors and that's in that case, which can of course also happen the longer the process here is. Here a very small sketch of what you do during training. So in the first row here is, well, what you already know from before is that you train a model, right? And then you, perhaps during testing, you test that model. But here in pipelines, you not only learn the model, but you also make sure that the data pre-processing, like scaling, encoding, feature filtering, is also always the same. And you record this and do the exact same steps with your test data set. So you scale with the same scaling factors, you encode with the same factor levels, and you select the same features that you have also selected for training. And then, once you have done all this, you can of course use your machine learning model to predict new unseen data points.